Today we're going to start a lesson on buffers and the Henderson-Hasselbalch equation. We're going to start off with a little chemistry joke. Why did the acid go to the gym? We all would like to go to the gym right now, right? So to become a buffer solution. So we're going to talk today on what is a buffer and how do we do calculations with buffers. Before we begin buffers, let's do a problem that we had from last unit. If we wanted to know what is the pH of a 0.3 solution of acetic acid, so we would need to think about what do we know about acetic acid. Well, acetic acid is not one of our 7 strong acids. This is a weak acid. And so it doesn't break down all the way. In fact, it doesn't break down very well. So it's going to get to a point of equilibrium. And we know that because we have a Ka. So that means we're going to have to write this particular equation. Or do an ice table. So we've got acetic acid, and it breaks down, and we get hydrogen ions, and we get acetate ions. So the 0.3 is here. It's going to lose a certain amount. And these start out our original ions, and we're going to add a certain amount. And our ratio is a 1:1. The coefficients are going to come back in each unit. So right now we're still 1:1. And so we're going to end up with x squared over the 0.3 minus x, setting it equal to the Ka of 1.8 times 10 to the negative 5th. And because this is to the negative 5th, this beats the 5% rule where we get to take and get to mark out that minus x there. So we can cross multiply, take the square root, and we can get our x to equal 0.00232. And if I trace that back up to my equation, I will see that, my mouse to go with me, that is my hydrogen ions. So to find the pH, I can take the negative log of 0.00232, and I'll find that the pH of this particular solution is 2.63. It's still quite a bit acidic there. And to do our percent ionization, which is how much of it is breaking down, what percentage it is breaking down, it's always the x over the I. So we're going to have the 0.00232 divided by molarity. Divided by 0.3 molarity times 100. And we'll find that this breaks down only 0.77% of the time, not 77%, which is why we do consider it a weak acid. So this was all last unit. That doesn't go away though, because we still need to be able to figure out what the pH of just a weak acid would be. So we're going to move on. So now it says, what would the pH be if we have a solution of, we had 0.3 moles of acetic acid. Okay, well, we just had a 0.3 molar. But for some reason, instead of putting it in just normal water, which is what we just did, we're going to put it in some sodium acetate. Now, if I try to write a reaction between these two, so don't copy this with me, I just want you to watch, and then you can start copying when you start looking at the problem. If I try to write a chemical reaction, sodium acetate, they're not going to chemically react because they share this common ion with one another. So we can't double displace or anything like that because they're sharing the acetate ion. So what we have here is a situation of where we have a weak acid, and we call this its conjugate base there. That's the conjugate base. And so we talked about acids and conjugate bases before. So these are not going to chemically react. So you should not be writing a reaction with those. But what's going to happen is the fact that this sodium acetate is there, it's going to cause an equilibrium shift. According to La Chatière, we're going to see a shift. So I'm going to start writing the equation just like I did a second ago. So we're going to disrupt this acid trying to get to equilibrium. So I'm going to go ahead and write it. Looking just like the problem before. Okay. So we would always put this in molarity. It is a 0.3 moles. It is a 1 liter solution, so it's going to be a 0.3 mole. This is still 0. But the problem here is that sodium acetate has some acetate ions. This guy right here is nothing more than a spectator. Sodium ions tend to be a spectator in a lot of reactions. So we don't need to worry about the sodium part of that, but the acetate part of that. And we do have some. So we have a point, and it's 0.3 moles 1 liter. We have a 0.3 mole in the solution there. So this guy being present is going to shift our reaction back this direction. So because according to Hasselbalch, if you add some of one ion, it shifts the reaction in the other direction. So that's what we're going to see. And this acid's not going to be able to break down as much, so we're going to see the pH not be as high. This is also a basic salt. That's a conversation that we've had before too. This is a basic salt that's going in, so this is going to elevate our pH as well. So we're going to see lots of chemistry reasons of why our pH is going to be higher. The fact that this is 0, I do know I'm adding X here, and I am adding X here. I am going to be subtracting X here. So we're going to get 0.3 minus X, and 0.3 plus X. And so now we've got on top an X times a 0.3 plus X. On bottom, a 0.3 minus X, and we're going to set that equal to the Ka, which is 1.8 times 10 to the negative fifth. So I can get rid of the minus X and the plus X because of this negative fifth 5% rule. Now we got something unique. 0.3 over 0.3, well that's just 1, so they're canceling each other out. So I know real quick my X is 1.8 times 10 to the negative fifth. So pH, again, that's the H plus concentration there. So pH is the negative log of that. So our pH for this instance is 4.74. So in regular water, that same amount of acid was 2.63. And now that we put it in some water that has some of these ions, you can see this basic salt is elevated its pH. Let's look at the percent ionization. So it is your X over your initial, which was 0.3. And we are now going to see that the percent has gotten a lot lower. So a second ago, it was 0.77, and now it's even breaking down less, again, because of that common ion. This is known as the common ion effect. So if you put something in a solution and they share this common ion, if that one of the substances is trying to reach equilibrium, and when that it doesn't fully break apart, then you can get a disruption. So the common ion effect is a shift of the ionic equilibrium caused by addition of a solute that provides an ion that is common to the equilibrium. And so they both share the acetate. So this is what would happen if we add sodium acetate to the solution. It did cause a shift that direction, so the equilibrium composition would shift left, and the degree of ionization decreased. We saw that. We saw it go from a 0.77% to a 0.006%. And we saw the pH increase. So that is some results of that common ion effect. So that leads us to the discussion of the buffer. So I would have you write this down. What a buffer does, it has a weak acid and its conjugate base. So that's important to share a common ion, or it's a weak base and its conjugate acid. So that's going to be very important for you to kind of understand. So at no point did I say strong. So a weak acid and its conjugate base. Another way we could say that is it's salt. We're going to be talking about the salt. Or a weak base and its conjugate acid, also it's salt. So those are what makes a buffer. And so a buffer doesn't want to change pH. It's kind of trying to stay within a certain range. We have different buffers. We have things that will buffer around 7. So if we're buffering around 7, it will always try to stay really close to 7. I have pH buffers of around 4. It's always going to try to keep the pH really close to 4. And different organisms live in different environments, and that's why buffers are important. You have buffers in your body, and different organs in your body require your pH to be at different levels. Like your stomach is so much different than your blood, and so we've got buffers all in our body. And unfortunately, we as humans do things to our bodies, and the buffers try to counteract that, which is a good thing. So again, we're going to look at some of the math with it, but a buffer is trying to resist pH change. And so the reason it can do that, it has either an acid or a base component, so it can chemically react with one or the other to basically counteract what you might add into a solution. So I've uploaded this PowerPoint, but here's some things that you'll start to understand when we start working through the problems. But we're going to be trying to figure out which buffer is the best. So when you select the buffer, we're going to be looking for something where its pKa is close to its pH. You don't know what that means yet, but it'll start to become clear as we start working through the problems. And buffers are most effective when the concentration of the acid and the base are about the same. So a 1-to-1 molar concentration, so 1 mole to 1 mole, or 0.3 molar to 0.3 molar. I would like you to know that your blood buffers between, this is your blood, there's not, different organs in your body are different, but 7.35 to 7.45 is the way our blood buffers. So I love this little illustration. Here's our normal pH in those ranges, slightly basic. If we go lower than 7.35, that is what's known as acidosis. Anything higher than 7.45 is called alkalosis. And those are really important terms in the medical community. Alkalosis above 7.45 in the blood, and below 7.35 would be acidosis. So I would kind of like to know that as well. If we go, this is known as the Henderson-Hasselbalch equation, probably my favorite equation in chemistry. So I would suggest you write this down. You should have to remember this. So this is the Henderson-Hasselbalch equation. If we can recognize that we have a buffer solution, we really are not going to need to do a rise. We could actually use this equation. So pH equals the pKa plus the log of the base over the acid. Now this could be a conjugate base over a weak acid, or this could be a weak base over a conjugate acid. So basically this is only used for buffers. Okay? So anytime you put a little p in front of something, it means negative log, such as pH, it's a negative log of H. Well, pKa means negative log of the Ka. So that's another way to look at it. So instead of pKa, it's negative log of the Ka. So real important equation. Love this equation. So let's look. It says, what is the pH of a buffer that is 0.12 molar lactic acid and 0.1 sodium lactate? It's given us the Ka for lactic acid to be 1.4 times 10 to the negative 4. So one thing we could do is we could rise, or we could write, oh, this is a buffer. I don't need to rise it. I could use the Henderson-Hasselbalch equation. But even though if it didn't say these words, because it sometimes won't say, this one does, but if it didn't say, I would know that it's a buffer because of this. This is a weak acid. And then sodium lactate, you see that they both would contain lactate. There's that common ion. So this is a salt. Sodium lactate is the salt of lactic acid. Or we would say this is the conjugate base. That is the conjugate base of that weak acid. Again, sodium is just going to be a spectator in that little reaction going on, messing up equilibrium. So, oh, this is a buffer, so I can use this equation. Negative log of 1.40 times 10 to the negative 4 plus the log, now go to the side, base is on top, doesn't matter if it's a true base or a conjugate base, always base on top. So this is the equation, always base over top, always negative log of Ka. So negative log of Ka, base on top, and the base is 0.1, and the acid is 0.12. So take a second, plug that in your calculator, and see what you get for I put my page in. So see if you can get what that would be. I get 3.77. That's our pH. So love this equation. Very nice equation. The other alternative is to write it. You could do just like we did in number 2 and write the equation, putting that underneath the acid, that under the lactate, and write an equation. This is just so much simpler, and I do really like this equation. So it says, let's redo sample number 2 using this equation. Number 2 was a buffer. So a buffer, again, made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. So this one, number 2, was, and so pH is negative log, in that problem it was 1.8 times 10 to the negative 5th. Plus the log of, well, I didn't have to write it, you just write the beginning, the initial numbers. And it was a 0.3 molar sodium acetate and a 0.3 molar acetic acid. You notice these are the same, so these would be 1. If you take the log of 1, do that in your calculator. The calculator is going to say 0. So basically, negative log of that plus 0. So if they're the same concentrations, they cancel out. This is when a buffer does the best, when these are the same concentration. Remember that buffers are most effective when the concentration of the acid and the conjugate base are the same. So this was a real effective buffer. So we're going to get a pH, again, that was 4.74. We don't need to worry about that. So, anytime they're the same molarities, you just take the negative log of the Ka. So that's just showing that they're the same. You can cancel them out. Alright, this one gets a little bit more difficult. I highly recommend that you work this one with me. I am going to be looking at my page so I can write, and try to write most of my algebra steps for you so you can see. So it says, how many grams? There's a little bit different word there. So Henderson Hasselbalch is not in grams, so I'm going to need to find moles before I can get to grams. So how many grams of sodium lactate would you need to be added to the 0.15 molar lactic acid to make 1 liter buffer solution with a pH of 3.98? So again, our formula was pH equals negative log of the Ka, this one is 70%, plus the log of the base over the acid. So I'm looking for sodium lactate, which is the base here. So in math class, if you're trying to solve for one of these guys, you have to separate it. You have to go log of the top minus log of the bottom. It looks like that. So, because I'm looking for this one, I'm going to have to separate them. So this is a little bit more challenging of a problem, but in college we can do it. Okay, so here we go. We're going to start with what we know. We know 3.98 negative log, and our Ka is 1.4 times 10 to the negative 4 plus log of our base, I don't know that, minus log of our acid. I do know, and it's a 0.15 mole. Okay, so I'm trying to get this by itself. So I need to send that guy and that guy over this way. So to both sides, I'm just not going to show it over there. I switched to green. So I'm going to add the log of 1.4 times 10 to the negative 4 to both sides. That'll cancel that one out. And then I'm going to add log of 0.15 to both sides. And that'll cancel that guy out. Switch back to it. You're going to put that in your calculator. When you hit log, make sure to always close that parentheses out before doing this one, because it will give you the wrong answer. So make sure you close that parentheses out. This is what I'm going to look over there. I got this side to be a negative 0.6977807. And then this is the log of the base. How do you get rid of log? Well, it's called anti-log. You get second log. So that makes that little 10 with the house top there. So to get rid of the log, I do the 10 house top. You should be familiar with that by now. And so my base is 0.201. That is the molarity of the sodium acetate, the base. It's not sodium acetate, it's sodium lactate. Sodium lactate. And they gave us lactate in the problem before. So, sodium lactate was NaC3H5O3. Lactate's not one that you have to know. So, okay, so I need to figure out how many moles this would be. So if we think about it, molarity, again, that is the moles in my line. So to find moles, it is molarity times liter. So I'm going to multiply that by the liter. It equals 1 liter. So that is going to be my, that's how many moles of sodium. This one's a little bit more challenging, I understand. Bring moles down. Go into grams. Every 1 mole, we would add up how many grams. We would use molar mass. 1 sodium, 3 carbons, 3 hydrogens, 5 hydrogens, 3 oxygens. I got a molar mass of 112. Again, do this math for yourself. See if you can get this answer. Okay, so I've got 22.5 grams of sodium. There we go. So, that one was pretty tough. We could do it. Okay? Well, let's move on. So here on the PowerPoint is the directions for what we're about to do. So we just did the pH of just a buffer itself, but buffers are great. We build the buffers, but the reason we use buffers is so that they resist pH change. So we're going to see how they resist by doing what we call a neutralization reaction. So I'm not going to read this to you, but if you need to go back to the PowerPoint and read, you can see that we've got the steps there. So we're just going to work through it. So let's look at the next lesson. So we just did a buffer. A buffer's made of adding. We just did this. This was, go back and look at number 2. This was problem number 2. But and we found that pH of that buffer was 4.74. Again, we did that. That's problem number 2. What we're going to look at, what if to this buffer we decide we want to add some sodium hydroxide in there. So we know that the pH of the buffer was 4.74, and we're going to add some 0.1 moles of sodium hydroxide. The pH of that would be about 13. Okay, so 0.1 molar would be a pH of about 13. We'll want to see what that new pH. So here's going to be my suggestion. We kind of work this out. We have two parts of our buffer. So your buffer has these two things in it. It has acetic acid. That's our acid part of the buffer. It's weak acid. And then we have the base part of it, which was sodium. Sorry, sodium acetate. Switch that. Okay, and so this is our conjugate base. That's our buffer. And we know it's buffering 4.74. So what I'm adding into it is now sodium hydroxide. So what I need to do is to figure out what reaction to write here. I know the sodium hydroxide is going to react with one of these two things. And so sodium hydroxide is a base. And a base is not going to react with a conjugate base. Do you see that they're both sharing sodium? They're both sharing an alkali metal. They're not going to react with one another. But this base that I'm adding is going to chemically react with this acid. So, because the buffer has both parts in it, the opposite thing is going to react. So what we're going to do is we're going to start out with the thing that I'm adding. So I call it the invader. We're going to start with the invader. And we're going to react it with the part of the buffer that's going to be opposite. This is a base, I think the acid. Okay, looking okay. This is a double replacement reaction. And so what happens is those front ions, those cations, basically switch places. Now here's what we're going to do. Not two arrows, one arrow. The one arrow being that it's going to chemically react, and it's somebody's going to go to zero, because the job of the buffer is to make things go away. And so this is not an equilibrium, it's a neutralization reaction. It's a reaction that's actually going to stop once something's gone. So unlike equilibrium, things go back and forth, this one is going to eventually just stop. So that's why we're going to have one arrow. So let's just double display. Sodium is going to end up with that acetate. And then hydrogen and hydroxide are going to hook up. Hydrogen and hydroxide. That is water. Hydroxide being water. So now, I would highly recommend to do this. So first off, let's switch to it. This is going to break apart because it's a strong base. Or alkaline metal. All alkaline metal compounds break apart in water. This stays together because that is a weak acid. It doesn't form a solid, but it doesn't 100% break apart either. It just really breaks apart. This is going to break apart because it's an alkaline metal compound, and then water we always find. So we get our spectators out of there. You can see that's our spectators. So, looking kind of familiar, we're about to switch letters up on us. This is going to be what I call a reaction table, not a rice table. This is called a RICA table. RICA table, reaction table. What's the difference? Well, one of the differences was one arrow. Okay? The difference there, something's going to stop. The biggest difference is the unit here, is moles. And for this unit, we're going to be on the RICA table. So like, oh, I have an acid and base reacting, that's a neutralization, RICA. Acid base reacting, RICA. So that's what we're going to know. Alright, we're going to go back up and see how much did we have of the sodium hydroxide? We had 0.1 moles of this sodium hydroxide. These are in moles, it's in moles. How much of the acetic acid? Well, we had 0.3 moles. And we had some sodium acetate, because that's a buffer. We had some of this. This guy was there. Water, it's there too. It's an amount, but we don't really care about water. I mean, we really do, especially now. But for this, we're not going to worry about the water, since this will go underneath that. Okay? It's not going to affect pH, which is what we're going to look at. All right. So, not worry about this guy over here. The job of the buffer is to make this guy go away. So you look at your two reactants, and whichever number is the smallest, which in this case is 0.1, that's how much you're going to lose. So 0.1 minus 0.1 is 0. This is why it's a Ricca table, because somebody has just gone to 0 on us. Okay? It's not going back and forth. None of him was there. We didn't go back the other direction. So smallest number goes away. If I lost 0.1 of this guy, I also lost 0.1 of this guy. It's a 1-to-1 ratio. So this is 0.2. Now if I added, the arrows go in that direction, I am losing reactants. And I am making products. And it's a 1-to-1 ratio. Alright. So at the end, after the A stands for after the reaction. After the reaction has completed. So no equilibrium. Do you notice what's left? We've got some weak acid and we have some conjugate base. So what is left? Well, still our buffer. Our buffer is still there. So we're looking for pH. We can still use the Henderson-Hasselbalch equation. Negative log of the Ka, which is 1.8 times 10 to the negative 5th, plus the log of the base. This is the acid, so there's the base, which is 0.4 moles. Oh, I should say, Henderson-Hasselbalch, your unit here, because right here is going to be a proportion, it can be in moles or molarity. This is a ratio. It just can't be grams. So moles or molarity. So 0.2 moles. And you can put that in. And I got 5.8. So it was 4.74. I put something about 13 in there, which is quite a bit of base, by the way, and it only went up to 5.0. So the buffer was still there, still try to hold the pH pretty consistent. Alright, so this was a buffer putting a strong base into the buffer. So the strong base reacted with the acid, and it still was there. When you go past the buffer capacity, that would have been an instant if we had added 0.4 moles here. If we had added 0.4, our smallest number would have been the acetic acid, and we would have what we call busted the buffer, and the pH would have shot way up in this case. That was in the body with lead. So the pH just goes shooting way up or shooting way down. So now we're going to look and see what it would look like if we were to add an acid into this. So same scenario, same buffer, but this time we're going to add hydrochloric acid into it. So buffer, remember it had the acid part, so this is what I've got in my buffer. So it's got the weak acid and it's got conjugate base there. And I'm adding hydrochloric acid. So hydrochloric acid is an acid. So two acids are not going to react. So I'm not going to write my equation with hydrochloric acid and acetic acid. I would get a reaction because they would both have that H. So I'm going to choose this, the conjugate base, to write my reaction. So I'm going to start with my thing that I'm adding, which is HCl. I'm adding sodium acetate, 1 arrow. We are going to double displace, so we're just going to switch those guys out. So you're going to get sodium chloride and acetic acid. Alright, so if we do net ionics, we'll get green. That's going to break apart, strong acid. That's going to break apart alkali metal compound. That's an alkali metal compound in water, and that is a weak acid. So our spectators, hydrogen not a spectator, chlorine is a spectator, or an ion. Sodium, also a spectator. Acetate, not a spectator. So here's why we wanted to do that. The reason we wanted to do that is because doing Ricket table again, because it's an acid-base reaction. Do you see this? This is a spectator. That's a neutral salt that's forming there, so it's not going to affect the pH. So just like water, I get to scribble underneath it. This is the reason we do that. Okay, that's the whole reason. So we started out back in that problem, 0.5 moles of hydrochloric acid. So 0.15 moles. The sodium acetate, we had 0.3 moles. And acetic acid, we have 0.3 moles. Can't forget that guy over there. Smallest number is going to go away. It is the hydrochloric acid. And it's 0.15. If we subtract here, we add over here. And 0.45 moles. Okay. Alright. After the reaction, do we still have buffer? Well, this is a conjugate base, so yes. And this is a weak acid, so yes, we still have buffer. Why is that important? Because you can still use Henderson-Hasselbalch equation, which again is my favorite equation. Alright, so we got to decide which one's the base. Well, I just told you that was the base, 0.15 and 0.45. And then we would, in the calculator, add that 4.26. So the pH did go down. It was hydrochloric acid, which had a pH of 1, and it brought our 4.74 down to 4.26. So not a huge amount of drop down there. So that's pretty much buffers and how a buffer reacts when you add in an acid or a base to the buffer situation. Please email me if you have any questions or concerns about this lesson.